Now that you know how to solve a system of linear equations, let's take a look at the two special cases that arise when solving systems of equations. Remember, each equation in your system represents a line. So far, all of the systems that we've been solving have been independent systems, two separate lines that crossed in one point. They had one solution. There are two other possible outcomes for solving a system of equations. We could have two lines that are parallel. In that case, the two equations are still independent, but the system is not consistent because there's no point that lies on both lines. The third situation would be if we had two lines that actually lie on top of each other. In other words, they're the same line and they have all points in common. A system like this would be considered consistent because all the points lie on both lines, but it would be considered dependent because these two lines are not separate lines. They're just the same line written in a different form. So these are the two special cases that we're going to look at in this lesson. A system that is inconsistent, it has no solution, but its equations are independent. And a system that is consistent, it has solutions, but its equations are dependent. They're the same equation. Here we go. In this first example, our two equations are 2x plus 5y equals 3 and negative 8x minus 20y equals negative 12. From looking at this system, you wouldn't necessarily be able to tell that it's a special case. So let's go ahead and start to solve it the way that we normally would. We can use substitution or elimination. Here, I'll use elimination since it looks like it would be easy to get my coefficients to be equal but opposite. If I multiply the top equation by 4, I'll have a positive 8x, and then in the other equation a negative 8x would cause my x variable to be eliminated. Multiplying by 4 on both sides gives me 8x plus 20y is equal to 12. And I'll just rewrite my second equation because it didn't need to change. Now we add the two equations together. Look what happens when we do that. 8x and negative 8x are eliminated. That's what we wanted. But now when we add the y's, 20y and negative 20y is also eliminated. So the left-hand side is equal to 0. Let's go over to the right-hand side. 12 and negative 12, well, that's equal to 0 too. So everything has been eliminated. And all we're left with is an equation that says 0 equals 0. This is what lets you know that this system is a special case. The equation 0 equals 0 is always true. All our variables have dropped out. So this equation doesn't depend on the value of x or the value of y. 0 is always equal to 0. This is an equation that's always true. When you're solving a system and you end up with an equation that's always true, that's your indication that these equations are dependent. This means that these two equations were actually the same equation, just written in a different form. If we were to graph this line and then graph this line, they would lie on top of each other, just like in this case here. So we have a system whose equations are dependent and the system itself is consistent. All of the points on one line also lie on the other line. That means we actually have an infinite number of solutions. Let's look at the next case. These two equations are 5x minus y equals 8 and 10x minus 2y equals -1. Again, we're going to begin solving just as we would for any other system. Looking at these two equations, I want to use substitution, since it looks like it would be easy to get this y all by itself. First, I'll need to subtract the 5x from both sides. That leaves me negative y is equal to negative 5x plus 8. Now, I'll need to multiply both sides of this equation by -1. That gives me y is equal to 5x minus 8. Remember, when you're multiplying by -1, the sign of each term changes. I have y by itself, so I'll take this expression and substitute it into the other equation. That gives me 10x minus 2 times, and here in place of y, I write my expression, is equal to -1. Now we solve for x. First, we need to multiply by the -2. -2 times 5 gives us -10x. -2 times -8 gives us positive 16. Now we continue to simplify. 10x minus 10x. Here it is again. 10x minus 10x is 0. So on this left side, the x's cancel out and we're left with 16. The right-hand side is still -1. Now we have a problem. 16 is clearly not equal to -1. This equation is false. This is our indication that this system is inconsistent. It has no solution. There is no point that lies on both of these lines. So if we were to graph those two equations, they would come out to be two parallel lines. And that's the other special case. In this situation, as we were solving, we ended up with an equation that was not true at all. All the variables canceled out again, and here we're just left with an untrue equation. So with these two special cases, you're always going to see that the variables will cancel out or be eliminated, and you'll either end up with an equation that's not true at all or an equation that's always true. In one instance, that tells you that there's no solution to the system, and in the other instance, it tells you that the two equations are dependent.